Now let's look at several examples of factoring binomials that are differences of squares, or may not be, but trying to decide when they are and when they are not. So here we have a binomial, and it does not appear to be a difference at all. It's a plus, which is a sum. So we may be tempted to try something unusual here. However, this polynomial is not, or this binomial is not in descending order. So the first thing we should do is move our terms around to make it positive 36z squared minus 25, and now it is a difference. And so there's only two terms here, so the only way it could possibly factor would be as conjugates. And so I have to have the same thing in both sets of parentheses, one with a plus, one with a minus, because that would give us a negative 25, and it would make our middle term cancel out, which this has no middle term. So to get 36z squared, we'd use 6z and 6z. And to get negative 25, we'd do positive 5 times negative 5. And since these are conjugates, there is no middle term, so we're done. Okay, no problem. Let's try another one. Okay, so here is a binomial, but it's not in descending order, so we move it around. And we notice something different about this guy. This one's not a difference even when we put it in the right order. It's still a plus and not a minus. So we still think though, okay, there's no middle term, so I have to use conjugates to factor it. So I use 6z times 6z to get 36z squared. And to get the 25, I use 5 and 5. And since there's no middle term here, I have to do a plus 5 and a negative 5. Now the question is this correct? Well, 6z times 6z does give us the 36z squared. So that's good. However, the positive 5 times the negative 5 gives us negative 25, which is not positive 25. So that cannot be right. So now we're thinking, okay, what do I do? There's no middle term, so I have to use conjugates, but if I use conjugates, I get a negative 25 instead of a positive 25. The answer to that question is this guy doesn't factor. He's called prime. This polynomial does not factor because it's not a difference. So whenever there's no middle term, you have to have a difference as well, a minus, because conjugates always will give you a minus for the last term. So this polynomial is prime. Let's do another. So here we have another polynomial. It is a difference, however, it is not in the right order. So if we move it around to get negative 36z squared plus 25, now it's not a difference, it's a plus. But we notice that the first term's negative. Anytime your first term's negative, when it's in the right order, factor the negative out along with your GCF. Well, there is no GCF except for 1, so we're going to factor out a negative 1, which changes negative 36z squared to positive 36z squared, and positive 25 changes to negative 25. And now, inside, we have a difference of two squares. So I carry my negative 1 down, and I factor the difference of two squares using the conjugates 6z plus 5 times 6z minus 5, and we're done. So these problems are all very similar, but you can see how they work out a little differently. Let's do another one. Okay, we look at this binomial, and the good news is it's in the right order. But these are not perfect squares, right? So we don't know how to factor it, but you always need to remember, after you look for the right order, you look for a GCF. And I can see that between the 20 and the 45, I could factor out a 5, leaving behind 4z squared minus 9. And now this remaining binomial is a difference of two squares, so it will factor using conjugates 2z plus 3 times 2z minus 3. And now we've factored it. Let's do one more example. Now this type of binomial confuses people all the time. There's no numbers, so it can be confusing. But don't let that disturb you. Just go like you always do. Put it in the right order first, negative x to the 6th plus x squared. And then look for a GCF. I see that I can factor an x squared out, But since my first term's negative, I'm going to factor out negative x squared instead of positive x squared. When I factor that out, the signs inside here change. So the first term is going to be positive. And when I factor x squared out of x to the 6th, that leaves behind x to the 4th. And when I factor x squared out of x squared, I get a 1 with the sign change because I factored the negative out. So now I've got my GCF, my negative GCF here. This is a difference of squares that can factor, because in order to get the x to the 4th, I can use x squared and x squared. Now a lot of people get confused by 1. Well, 1 times 1 is 1, right? So it's really pretty simple actually. And I need a negative 1, so I need positive 1 times negative 1. And there we go, we factored this binomial. Now it's a little tricky. When I look at this step, I need to ask myself if I'm done. In the previous problems, we've been done because each of these has a variable to the first power, and you can't break a variable down if it's raised to the first power. Over here, though, the variable's squared. So I look at these guys, and x squared plus 1 is a binomial, but it's not a difference. There's no minus anywhere, so there's no way I could factor it using conjugates. So x squared plus 1 does not factor more. However, x squared minus 1 does have a minus, and x squared is a perfect square and 1 is a perfect square. So I can factor it down further, right? I can factor it using x times x to get x squared, and positive 1 times negative 1 to get the negative 1, and to make the middle term cancel out. So don't forget that as you factor, you always need to keep looking to see if anything factors further. Now I know x squared plus 1 doesn't factor, as we said before, and now these are each to the first power, so they don't factor either. And now we're completely done. All right, I hope those were some good examples for you and you understood them all.